Hey everybody, my name is Mel Hanna. I am a senior data scientist at Stable Auto, and I am also a member of Climate Change AI's core team and the summer school team. Today I'm going to be talking through the tutorial on tracking carbon emissions from training ML models. So let me go ahead, I'm going to share my screen. Hmm. Okay, so let's walk through this notebook. Um, Just to give a quick overview of the goals of this tutorial, by going through this notebook, you're going to learn how you can measure your emissions using a Python package called CodeCarbon and different strategies that you can use to potentially reduce your carbon footprint when you're training machine learning models. The target audience for this tutorial are folks who have some experience with data science, just the basics in terms of understanding, how to train a model. But we are taking things, at a pretty introductory level, so you don't need to have years of experience to get value out of this tutorial. If you're running this tutorial in Colab, the software requirements should be taken care of for you. We do import and install some packages later on, but again, if you're using Colab, you should be able to run this notebook as is. We do recommend, however, that you enable GPU. We are running some models later on. It will be very helpful to have a GPU access in order to speed things up. There are some instructions here on how to enable GPU in Colab if you're unfamiliar. Okay, so let's take a moment to install these dependencies. I am not going to be running code live here today, but the output is viewable within the notebook. So we're going to be installing CodeCarbon. This is the package that's going to allow us to determine the amount of emissions that are produced from running our code, as well as some other dependencies that are needed for CodeCarbon and for doing some optimization later on. We're also going to create a directory here called CodeCarbon. This directory is going to contain the emissions data that we're going to produce every time we run an experiment. So you'll see that later on. All right, here we are just importing some pretty standard data science libraries here, and then just setting some random seeds. Okay, so let's talk about the background around this tutorial. The climate impact of machine learning has three different levels that are really depicted here in this diagram. So there are system level impacts, which is this white outer layer here. We have application impacts, the intermediate level, and then computing related impacts. Now, this tutorial is going to be focused on computing related impacts, but it's really important as you are going to approach an ML project that you keep these other levels in mind. So let's talk about those in more detail. System level impacts are considering the societal implications of machine learning. And really, these probably have the greatest impact in terms of greenhouse gas emissions. So a really good example is implementing a recommender system that might increase the demand for physical goods, especially if we're, relying on some heavy manufacturing processes or shipping these goods. Obviously, that's going to be producing a lot of greenhouse gas emissions. So it's just thinking deeply about how your model may be used in wider societal context. The next layer here is application related impact. So how is your model going to be used within a business or within society? So, does your model enable carbon emitters or is it reducing the expansion of renewable energy? So an example is, machine learning has been used pretty widely to help identify new oil fields for exploration and also to help within the livestock industry in terms of tracking within factory farms. So again, this is just keeping in mind when you're asked to build a machine learning model that you're thinking about how it's being used and whether or not that's helping or hindering with the climate crisis. But today we're going to be talking about computing related impacts of your machine learning model. There are two different components of this level, and that's embodied and operational emissions. So embodied emissions are going to be the climate impact of the hardware you're using, such as material extraction and manufacture of computer chips. Operational emissions are the emissions that are associated with actually running your code, so creating and productionalizing an ML model. Again, that's what we're going to be talking about today, but it's important to also think about embodied emissions as well if we're taking the entire life cycle into account. So there are, the ML life cycle is its own thing. We start by preparing data, then develop a model, deploy the model, and then start over again because we are continuing to improve the model as we know more. And again, we're going to need to take each of these stages into account when considering our emissions impact. All right, just a quick note here on, thinking more broadly, how much of a problem is this, right? In terms of all the contributors to the climate crisis, is the fact that I'm training a machine learning model really, making that much of a difference? So some quick stats here in that the field of information and communications technology accounts for about 1.4% of global greenhouse gas emissions. About 2/3 of those emissions are related to the operational side of things. So it's not completely insubstantial, surely not the largest component, but it's something that I'm assuming most folks who are listening to this walkthrough, we're doing this in our day-to-day lives. And it's a way that we can have an impact when we are going about our work. A good case study here is around ChatGPT, as it's something that I'm assuming almost everybody has used at least one point over the past year or two. So let's break down what ChatGPT's contribution is in terms of emissions. So as of last year in 2023, the underlying language model was GPT-3, and that the training process for that model consumed an estimated about 1,200 megawatt hours. And if we want to put this into context, the average American consumes about 10,000, 11,000 kilowatt hours in 2021. So the energy to train GPT-3 was the equivalent of adding about 121 Americans to the grid for 1 year. So not a huge impact, like surely we would prefer that it was smaller, but let's remember that the ML lifecycle is not just training a model, right? We are also deploying the model and making it available for users to make predictions or generate, in this case, different queries. So if we look at the production data here, ChatGPT saw almost 600 million unique visits in January 2023. There are some back of the envelope calculations here. They don't release this data, but we have been able to make some estimations that the electricity consumption during that time period was between about 1,100 megawatt hours and 23,000 megawatt hours. So that's between 1 and 18 times the amount of energy needed to actually train the model at the beginning. And remember, this is just 1 month. So it is really important when you are making these design decisions for your models that you not just consider training, but also think about how your model is going to be productionalized to ensure that you are doing so in the most efficient way possible. Okay. Now that we've gotten the background out of the way, let's talk about how we can estimate our emissions when we are training machine learning models. As I mentioned, we're going to be using a Python package called Code Carbon. It was put together in 2020 by a team from Mila, BCG Gamma, Haverford College, and Comet. And at its core, it is calculating, estimating really the emissions by looking at the hardware that you are using to run your code, and then multiplying that by the regional carbon intensity of electricity in your region or as used by your cloud provider. So let's break that down in more detail. Just a quick note here that there are many other packages that provide similar functionality. I have them linked here if you want to check them out. I chose to use Code Carbon because it is continually maintained and does a pretty good job of explaining how it has come to the calculations that it does. All right, so the first thing we need to do is initialize the Code Carbon tracker. So that's what I'm doing here. I'm just going to instantiate emissions tracker. I tell it to output the emissions data to that directory we set up before, and let's call it emissions.csv. So we're going to start the tracker, and we can see some output here, which we're going to break down in the following cells. But before we do so, let's talk about measuring our power usage. Let's define some common terms within machine learning, such as CPU, which is the central processing unit of your machine for general purpose programming. GPU is a graphical processing unit that allows us to work in parallel. TPU, a tensor processing unit, similar to GPU, but it is custom built by Google. And then RAM is random access memory, just temporary memory that a computer can access quickly. So I love this Mythbusters video. I think this is the best way to understand the difference between CPUs and GPUs. I definitely recommend you watching it. I think it's only like a minute long, but you'll see that GPUs allow us to set off multiple tasks in parallel, and it greatly speeds up computation time, especially when we're doing machine learning. And that is why we recommend that you use a GPU in this notebook so that we can more quickly train our models. All right, so quick background here as well, if we want to get into understanding how our hardware power is measured. It's using something called TDP, which is thermal design power, maximum amount of heat a CPU or GPU can generate. If you want to understand a little bit more about how to optimize, choosing a GPU or choosing a CPU, there's a plot here because if we think about a GPU is going to be speeding up our training process, which means that perhaps we actually have lower emissions because we are computing for less time, but GPUs are more power intensive. So it is a trade-off. It's definitely something you can look into and experiment with, but there is more research cited here if you're interested in learning more. Now, for this particular notebook, we noted here, this is Code Carbon's output from above. I just copied it down here. It's taking a look at what hardware I am running this Colab notebook on. And I had run this notebook back in April of 2023. So at that time, my RAM was about 12 gigabytes. 2 CPUs were found. This is the model that was used. 1 GPU, Tesla T4. So Code Carbon has information on these types of CPUs and GPUs, and that is what they're using in order to estimate the emissions from using this type of hardware. So definitely take note when you are running this yourself on what sort of hardware is being found by Code Carbon. And here we're just summarizing that information. So the other side of that equation, if we remember before, that Code Carbon uses is we want to look at the hardware, but we also want to look at the regional carbon intensity. So what is Code Carbon doing to estimate that? Again, running this in Colab, so we can take a look and see what region has Colab selected as my compute region because, as a cloud provider, I don't manually select this myself. And in this case, it selected Iowa. I am physically located in Chicago, so that's not far. But I will say every time I run this notebook, I get a new region. Sometimes I get Singapore. So that is one way you could try to reduce your emissions, is by finding a region where the uh, carbon intensity is lower. So Iowa is kind of middle of the pack in terms of US states for carbon intensity. But if I really wanted, I could try to just restart this until I get something that's a little bit lower. Here I note Vermont or Idaho have particularly low carbon intensities. But again, this sort of optimization is going to be easier if you have the ability to manually select the compute region. And in many cases, if you're not working on a cloud provider, you don't have any control over this. All right, so Code Carbon will also create a dashboard for you where you can put your emissions into context. So I'm going to stop my tracker. This is going to calculate the emissions that were created between when I started the tracker and then when I've stopped it. So here it's telling me some stats. I've done pretty much nothing since I started the tracker and when I stopped it, so I'm not surprised to see that this is such a small number. But if we wanted to, you can uncomment this cell and run it, and it's going to display a link that will take you to the Code Carbon dashboard, which I have done so before. I'm going to pull it up here. Again, we don't have any interesting data, but if you had run this, maybe after training a machine learning model, you'd see numbers that are not zero. But this shows us equivalence, right? So, if I had like 10 kilowatt hours, what percent of weekly American household emissions might that be? How many miles driven would that be equivalent to, et cetera? So this just allows you in a nice dashboard view to understand, how bad really are the amount of emissions that you're generating. Okay. So let's start talking about some Code Carbon experiments. Let's let you try to track our emissions from training a machine learning model. First thing we're going to do is we're going to generate our training and test set. We're going to be using the same data as the forecasting the El Nino tutorial linked here. This was used earlier in the summer school program. If you are watching this as part of the summer school for climate change AI. But if not, feel free to check out the tutorial to familiarize yourself with this, this data set and use case. We are trying to use historical sea surface temperatures to forecast the Nino 3.4 index. This determines the state of El Nino southern oscillation at any particular point in time. So the goal of the tutorial today, though, is really just to talk about machine learning training. So you don't need to understand the climate science behind this particular data set. We are going to download the data here and more downloads. And then we're just going to configure our data and set it up in a way that allows us to train a machine learning model. So no need to worry too much about this code. We'll be using it later on. All right, so one of the easiest ways that we can reduce our emissions is by choosing a simpler algorithm. Many times folks may go for a overly complicated algorithm such as, a neural network, when something very simple might suffice, like linear regression. So let's take a look at what the emissions impact would be by switching between a simple and a complicated algorithm. First, if we're going to train a baseline model of linear regression, we're going to set up an experiment, we'll call it linear regression, and we're going to create that emissions tracker from using Code Carbon as we had seen previously. So we're going to make sure that we're tagging this appropriately with the experiment name. And now we start our tracker. So any code run after this, the tracker.start, this is going to, it's going to be logged in our emissions aggregation. All right, so let's use that code I referenced earlier to configure our train, validation, and test sets. And we're going to train a very simple linear regression model using scikit-learn. We're going to make some predictions using that model. And we're going to calculate some model performance metrics on that model and plot a time series to see how well it's working. So here is the output from that model. The predictions are in orange, ground truth here is in blue, and we can see these don't line up very well. It's not the best model, but we stop our tracker and we see we have very few emissions from running this model here. So maybe a worthwhile trade-off, it depends. Let's look at the other side of this situation. We'll train a CNN, a convolutional neural network, and look at the emissions and the model performance from that. So again, this is the same data wrangling that we need to do. There are some additional steps in order to ready it for a CNN. We need to define the architecture for a CNN here. It's not a very complicated CNN. And define a class to train the CNN. And here we go. All right, let's kick off another experiment. We'll call it CNN. And we're going to assemble our training and test data again and train the model. So here we go, we're training the model. This is a neural network, so it's going to take a little bit longer than it did for our linear regression model. And this is why we want to use a GPU. All right, let's plot our predictions. We can see much better overlap now between our predictions and ground truth. So this is definitely a better model. And we stop our tracker and we see that we have 0.00036 kilograms of carbon dioxide equivalents that were generated from running this model. So putting that into context against the linear regression model, this is about 12 times the amount of emissions. So, you know, that's significantly more, but we did have better performance in terms of RMSE. Here's a side tangent as well. If you want to better understand that trade-off between performance of the model versus emissions, research has found a diminishing power law relationship between energy consumption here and model quality. So the power of this relationship is really small. So we're going to need to expend a lot more energy for marginal performance gains. So something to definitely keep in mind when you are making these design decisions. In some cases, an example I use here is a lung cancer detection model. We want to have the very best performance we possibly can for that kind of machine learning model. And in this case, you know, expending a lot of energy is going to be worth it. But maybe some other applications like a marketing churn model, something like that. Maybe it doesn't matter if we're getting like an extra 0.002% performance gain. So it's all about keeping the context in mind when we are going for that sort of optimization. All right, we can also plot here that trade-off just to help us visualize. So the bar chart here is the emissions. The dots here, the orange, are the RMSE, which indicates the model performance. So we can see for the CNN, much more emissions, but a lower RMSE, which indicates a better model. Linear regression is the opposite. So very few emissions, but worse in terms of performance. All right, we have our first exercise here. This is a chance for you to experiment with applying these learnings for yourself. I'm suggesting that you can try to reduce the size of the CNN by specifically removing the second linear layer, and then see what the impact is on emissions and on the model performance. So I'm not going to cover the solution. That's for you to find out, but this is a chance for you to play around with the code. All right. Oh, and I've got another exercise right here. This is maybe a little bit more of an advanced exercise. If you're already familiar with neural networks, you can try to use early stopping. If you're unfamiliar with that, early stopping is when we terminate training if our validation loss is not improving for several epochs. So um, if we were to apply early stopping, theoretically, we should maybe see some reduction in emissions. But this is another chance for you to put that theory to the test and see if you're able to reduce the emissions from that initial CNN. Okay. As mentioned at the beginning, when we talked about ChatGPT, it's really important to keep in mind what emissions are incurred from model inference, from making a prediction using your model. So let's use Code Carbon just to aggregate the emissions that are incurred from making a prediction with our linear regression model and from our CNN. So here we'll call the experiment linear regression inference and start our tracker, and we're just going to call predict, stop the tracker. Very small emissions here, as we'd probably expect. Now let's take a look at the CNN. We're going to do the same thing, but using our CNN to predict. And again, very small emissions, but we do see that the CNN emissions are larger than the linear regression. Now, it's a lot less dramatic than what we saw for training. And if you remember looking at the training output, that CNN is going to be training over multiple epochs. So training a neural network definitely usually is a lot more energy intensive than something like a linear regression model. So you're not going to see a huge impact in terms of your algorithm choice on inference. But if you are working with a model in which you're expecting to see a lot of inference, again, ChatGPT is a great example. There's a lot of users running a lot of queries through that kind of model. This sort of difference here is going to make a difference in terms of your emissions. So something to keep in mind depending on your use case. All right, so we talked about how you could reduce emissions from choosing a different algorithm or adjusting the architecture of your neural network. Let's talk about another strategy for reducing emissions in terms of hyperparameter tuning. So if you're unfamiliar, hyperparameter tuning is when we adjust the data that governs the training process itself. So the number of layers in a neural network is an example, but there's many other hyperparameters that can be tuned within a typical ML model. And we want to try to find the optimal combination of these hyperparameters that give us the best model performance. Now, tuning and searching for hyperparameters can be a intensive process that can produce a decent amount of emissions depending on the space we're searching in. So let's look at some ways we can reduce those emissions and be more efficient with our hyperparameter search in general. We're going to be using a Python package called Optuna to help tune our hyperparameters. So there's some information here about how to set up Optuna and define it. I'm not going to go into great detail, but you can take a look if you're more interested. So this is the code that's going to do that for us and help us look for optimal hyperparameters. Again, we're using the same data we did before. So there's nothing new here in terms of understanding the use case. But we are going to be using something called TPE search, which is tree structured Parson estimator algorithm. You might be familiar with searching for hyperparameters via grid search, where we would just search for every combination of hyperparameters. It's obviously very inefficient to do this. So TPE is a smarter way to go about it. It is also the default hyperparameter sampling method in Optuna. So TPE at a very high level is using a probabilistic model to identify the next best set of hyperparameters to search. It's using a Gaussian mixture model. If you're interested, you can definitely spend some time here understanding this in more detail. But we are going to be using TPE in this initial experiment. So let's go ahead and create an experiment called TPE search and start our tracker. Now, the TPE algorithm can't operate on a cold start. In order to fit that Gaussian mixture model, it does need some data. So we need to run TPE over some startup trials. That's what we're going to do here by setting startup trials to 5. And Optuna is going to create a study where we want to minimize RMSE in this case, and we set our sampler to be the TPE sampler. So let's go ahead and optimize, and we run our 12 trials here. We're searching for, oh, I'm sorry, I should probably, let me scroll up a bit and talk about the hyperparameters we're searching over. That would be helpful. Okay, so let's talk about the space that we're searching for in terms of tuning our hyperparameters. Again, this is the same use case we saw earlier with linear regression and CNNs. So we want to take a look and see what might be the optimal number of input time steps. And this is the number of time steps that we are looking back on to use for our prediction. So previously, I think we were using 1, if I remember correctly, in the linear regression and the CNN. But here I'm looking at 1, 2, or 3 as possibilities. We can also look at different learning rates for the algorithm itself. In this case, this is a log scale, so we're looking at 1 to the -4, 1 to the -3, and 1 to the -2. And then the optimizer, in this case, we have 2 choices, ATOM and SGD, which is stochastic gradient descent. Okay, so now that we have a better understanding of what the setup is for this problem, again, grid search, we try every combination of these, but we're going to be a little bit more intelligent, and we're going to look for what might be the optimal combination, and not search for all of these at once. Okay. So this now we can maybe better understand the output here that's being written from this first experiment. So we can see that the first few trials here, they tried num input time steps of 2, this learning rate, and then the ATOM optimizer. It's keeping track of what the best trial was with this RMSE value. So as we go forward, we can see that around I don't know, maybe this is trial 9 or so. It found the best trial was 7, and stuck with that for the remaining trials. And that's what we find output down here. These were the optimal set of hyperparameters, and this was the RMSE from that. And that if we do hyperparameter tuning, our model error is reduced by 15%. So this is taking a look at the model from the previous CNN where we did not do any hyperparameter tuning. Now that we have found better hyperparameters, we have a better model. That's great. But what was the emissions from running this kind of search? It's 0.004 kilograms of carbon dioxide equivalent. So, you know, not huge, but maybe we can improve it. All right, before we go on though to try some different methods, let's take a look at the fit from CNN trained with these optimal hyperparameters. Here we can look at the plot, and it does look pretty decent, but I do think there's probably still some room for improvement in this model. All right, so another strategy we can use is called hyperparameter pruning. And the goal here is to stop searching the space if we find that the intermediate objective value doesn't look very good. So for example, if we're training our CNN on a certain set of hyperparameters and the error by a certain epoch is really bad, then we're going to say, you know what, stop training. This is obviously not going to work out. It's not a very good set. Move on to the next set of hyperparameters. So that's what we call by pruning. We're just going to prune that trial and move on. All right, so what we're going to do in this case, I've added some new lines here on right here. So this is what we're doing if we should prune based off of the pruning strategy that we specify, which I will talk about in more detail. Then we're going to just remove it and move on to the next one. We're just going to call the new training code that uses pruning. And Optuna allows us to prune in 4 different ways. The first way is threshold pruning. So if the intermediate value is worse than some sort of specified threshold, we prune. You can also use median pruning if the intermediate value is worse than the median of the values in the previous trial. We'd prune in that case as well. And then there's 2 more as well. I'll let you read those and experiment with those, but you do have different options depending on what works best for your use case. In our case, we're going to experiment with percentile pruning. So that is going to prune a trial if the intermediate value is in the bottom percentile of trials within that same training epoch. So I am going to set it to be the 10th percentile. And let's take a look and see what happens to our hyperparameter search. So we're going to create a new experiment, and here we're going to create that new study, the hyperparameter search. And in this case, here we go. We define our pruner as the percentile pruner with the 10th percentile. And we're going to go ahead and we're going to kick it off again. And we have stopped searching at trial 5. So for trial 5 through 11, we pruned because we found that it was not getting better than the 10th percentile from those previous trials. So the emissions from running this pruned hyperparameter search, 0.002 kilograms carbon dioxide equivalent. And let's take a look and see what the hyperparameters were that we found from after pruning. So we do find different hyperparameters, which is interesting than our previous strategy when we did not prune. But the RMSE is very similar. So, same goal, even if we arrived at a different set. All right, let's talk about the emissions then from both the pruned and the unpruned studies. Pruning reduces our emissions, in this case, by about 47%. And that's not surprising because we did prune like half of our trials. So we would expect to see something like this. And also keep in mind too, I'm running this on like very small hyperparameter search space. These are really kind of toy examples, just so that this notebook runs pretty quickly and you're not waiting around for code before you see some results. But these strategies are going to be a lot more effective when you're doing, working with greater, larger data sets, or you have more hyperparameters that you want to be searching over. That's when these emission gains are going to really be valuable. Again, we'll just visualize what the impact is here in terms of emissions and model performance. Pruning, much fewer emissions. RMSE is, about the same, maybe a little worse here for the pruned hyperparameter set. Okay, we've got an exercise here again. If you want to experiment, you can use the median pruner strategy and just see, what is the impact in terms of the number of trials pruned? Are you getting the same model performance? What's the impact on emissions, etc.? So another chance for you to explore. And I have some other exercises here as well, just to finish it out. If you're still interested in understanding how you can reduce your emissions. You can adjust your hardware. So you could try running this with a CPU and compare to what the emissions were with a GPU. Is it better with the CPU? Is it not? I'll leave that up to you to figure out. And then, of course, computing or adjusting your compute region is another way that you might experiment within this notebook. But that wraps it up. So thank you so much for sticking with me throughout the walkthrough of the tutorial. I hope this helps and inspires you to start tracking the emissions within your own code and to write more efficient machine learning training code in general. Thanks again.